Imagine for a second that you've got a massive mountain of data. And it's not just sitting in one place, it's scattered across hundreds, maybe literally thousands of independently sorted lists. Your job? To combine every single one of them into one, flawless, continuously sorted timeline. I mean, it sounds simple enough, right? At least until you realize the sheer computing power required to constantly compare every single list against all the others, over and over and over again. How on earth do you do it without getting completely bogged down in endless linear comparisons? Well, welcome to this explainer. Today we're unpacking a really brilliant, highly optimized approach to exactly this problem, merging k-sorted linked lists using a min heap.
Okay, let's dive right into this. Here's our roadmap. We'll define the core coding challenge, review what it's like to merge just two lists, and then expose this massive k-list bottleneck. From there, we introduce our absolute hero of the day, the min heap, visualize how it executes, and finally, decode the time and space complexity.
All right, part 1, the core coding challenge, combining k-lists.
At its heart, the objective here is actually super straightforward. Given k independently sorted lists, we just need to stitch them together into one massive continuous list. You can see the initial state clearly, 3 separate sorted lists. The first starts with a 1, the second also starts with a 1, and the third starts with a 3. Our ultimate goal is that output list at the very end, weaving all those nodes together in perfect ascending order. Now, you might be wondering, why does this matter beyond passing a whiteboard interview? Well, because in the real world, this is exactly how distributed systems handle truly massive workloads. Think about log aggregation from hundreds of different servers or pulling together chunks of a heavily partitioned database. Doing this efficiently is absolutely crucial. It saves a staggering amount of compute time and resources.
Moving on to part 2. Merging just two lists. Let's build some intuition here.
To actually solve for k-lists, we kind of have to take a step back and build our foundation with the standard two-pointer method. The logic goes like this. Step 1. You initiate a pointer at the start or the head of both linked lists. Step 2. You simply compare the values of the nodes at those pointers. Step 3. Grab the node with the smaller value and add it to your output list. And Step 4. Just advance the pointer on the list you just pulled from. You basically rinse and repeat that entire process until both lists are totally empty.
And this perfectly illustrates it in action. We start with pointer 1 sitting on node 1 and pointer 2 sitting on node 2. We compare them. Easy enough. 1 is definitely smaller than 2, so we immediately move node 1 directly to our output list.
Because we pulled that node from the first list, we advance pointer 1 forward. Now pointer 1 is looking at node 3, while pointer 2 is still hanging out at node 2. We compare again. This time, 2 is the smaller value. So we pluck node 2 out and append it straight onto our growing output list. We just keep track in that exact logical flow. Pointer 2 slides forward to node 4. Now we've got a showdown between node 3 and node 4. Node 3 obviously wins that comparison, so it gets selected and added to the output.
Finally, to wrap up this two-list sequence, the first list is completely empty. That leaves only node 4. It automatically drops down to complete the sorted output. It's mechanical, it's highly efficient, and it works flawlessly for two lists. But here, my friends, is exactly where we need to shift our thinking.
Section 3, the k-list bottleneck, scaling beyond 2.
So the two-pointer method is a fantastic baseline. But what happens if we have 10 linked lists, or 1,000? Now, what's really fascinating about this is the core problem it creates. Combining two lists takes one comparison per iteration. But combining k-lists, naively, you'd literally have to look at the current front node of all k-lists just to find the absolute smallest one. That requires k comparisons per iteration. You're basically running a linear search across k items every single time you just want to add one little node to your output. As your data scales up, that linear scan becomes a massive system-choking bottleneck. There's just no way around it.
Let's move to section 4. Enter the min heap, bypassing the search.
Okay, if the problem is that linear search, we desperately need a data structure that completely bypasses it. A min heap is this incredible specialized tree-based data structure designed to do exactly one thing flawlessly. Keep the absolute smallest element right at the very top. It is the ultimate tool for our bottleneck. It's a total aha moment. With a min heap, you don't need k comparisons to find the smallest node at every single step. You literally just ask the heap for its top item and boom, you get instant access to the minimum value without any linear scanning whatsoever.
So, how do we set the stage? Our initial setup involves populating the heap with only the head nodes of all k-linked lists. We aren't dumping all our data in at once.
That would be chaotic. We just put the very first node of each list into the min heap. Notice the 1, 1, and 3 loaded in together. They are officially queued up and ready for comparison, and the heap guarantees that absolute minimum value is floating right at the top. Also, notice that little gray dummy node? That's actually just a standard, super helpful developer trick. It's a static anchor we use to easily build out the tail of our output list without having to worry about edge cases. Section 5. Visualizing execution. Let's look at the push and pop cycle.
Let's watch this algorithm come alive, because it's genuinely so cool. We kick things off by mechanically popping the smallest node right out of the heap. Because it's a min heap, we know instantly, without checking, that 1 is the smallest. We pop it out and connect it directly to our dummy output node.
Now pay attention, because here is the absolute secret sauce. The most crucial state change happens right here. Immediately after popping that node 1, we look at the specific list that the 1 originally came from, and we take its next node. In this case, that's node 6. We grab that 6 and push it straight into the heap to replace the 1 we just removed.
Let's move to the next iteration and see how this builds. Our heap resorts itself automatically, bubbling the new minimum right to the top. And what's at the top? The other node 1. We pop it right out and attach it to our growing output list. This cycle just continues beautifully. We push the next node from that second list, which happens to be a 4, into the heap. The heap does its magic behind the scenes and surfaces 3 as the new absolute minimum. We pop the 3, completely showing off how this data structure eliminates any need for manual searching. We replace the 3 with a 7 from its original list, and the heap instantly offers up 4 as the next smallest. The really crazy part is that this mechanical algorithm almost feels alive as it runs. We pop 4 next, completely bypassing any linear scanning. We are effortlessly draining k entirely different lists at the exact same time.
Let's fast forward the execution loop right to the very end of our data. The remaining nodes, the 6 and the 7, are sequentially popped out in perfect ascending order. Finally, node 7 is popped. The heap is completely empty, and we return our fully merged, perfectly sorted list starting right after that dummy node.
Finally, Section 6, Decoding Complexity. Let's do the time and space math. Now that we've seen the mechanics in action, let's talk hard numbers. We need to neatly separate the setup from the ongoing processing. Pushing the k head nodes into the heap takes big O of k log k time. Although, actually, you could optimize this to strictly O of k if you use a heap of 5 function. Then, for every single node in all the lists combined, let's call that massive total number n, we do a push and a pop. A heap push or pop takes log k time, so processing n nodes takes n times log k. When you sum it all up, the dominant term gives us a massive victory, a total time complexity of big O of n log k. And what about space? Well, because our heap only ever holds exactly 1 node from each of the k lists at any given time, the space complexity is strictly big O of k. It is incredibly lean.
Think about what we just did. We went from a sluggish, system-draining linear search to an incredibly sleek, logarithmic powerhouse just by changing our fundamental data structure to a min heap. So I really want to leave you with this final thought. If a min heap can optimize merging linked lists all the way down to big O of n log k, how might this exact same approach transform other massive multi-way merging problems you face in your own system architectures? Think about scheduling algorithms, stream processing, or real-time data ingestion. The structural logic you learned today really is a master key. Go see what else it can unlock for you.